and PhD from University of Anston, Birmingham, UK, and postdoctoral from University of Cambridge, UK, and Texas A&M, USA. He has authored and co-authored more than 250 technical papers, 8 books, including polymers in marine environment, cyclic beta-glucans from microorganisms, production properties and application from Springer, and drug design basics and applications, green chemistry and process, biochemical engineering, and biotreatment of industrial effluents, biotransformations and bioprocess, homologous catalysis, mechanism and industrial applications, and filed 8 patents. He is a fellow of Royal Society of Chemistry, London, and a recipient of Herdella Award for Excellence in Basic Research from Indian Institute of Chemical Engineers, and the Dow Professor M.M. Sharma Distinguished Visiting Professorship in Chemical Engineering at the Institute of Chemical Technology, Mumbai. He is in the editorial board of the Journal of Chemical Engineering, McGrath Publications and Phytomedicines, and a member of American and Indian Institute of Chemical Engineers. With this short introduction, I invite Professor Mukesh to deliver his lecture. Professor, the floor is yours.
Thank you very much for the introduction. Good afternoon, everyone. I will be talking about experimental design strategies that one can use for designing experiments. So let me first share my screen. Is my screen visible?
Yes, Professor.
Okay. So I am going to talk about design of experiments, various strategies we can use for designing experiments. There are something called linear designs, screening designs, second order designs, and so on. So we need to follow this strategy before we actually plan and start doing the experiments in the lab. So design of experiment plays a very important role in the entire process of statistical analysis of data. A design that's well organized, well planned, leads you to correct data when compared to a design which is ill organized or not well planned, actually. So that's very, very important. We need to plan our design correctly with the in a very scientific manner. That's what I'm going to talk about, actually. So there are some references. If one is interested, we can just take a screenshot of these references, which are very useful for design and analysis, industrial design experiments, and so on, actually. So this is a very, very statistical methodology, a systematic approach, and that's what we have to follow when you start doing an experimental design. So it's not very random, haphazard, not properly randomized. That's very important. So we don't say we will do these experiments today and then tomorrow we do some other experiment. So that becomes a very unorganized, ill-organized design. So the idea when we do the experiment is we want to know which are the important parameters. Okay, so imagine I will talk more about chemical and biochemical process because I am a biochemical engineer. So suppose I am doing a fermentation, for example, and I want to know whether temperature is important, pH is important, or carbon to nitrogen ratio important. So in order to find out which variables are very important, design is very useful. Optimize the product or process. So if I want to optimize the yield of a biopharmaceutical product, so I need to change many parameters. So design helps you to do that. Achieve robust performance. So the experimental strategy which I adopt, and I get a set of parameters which is optimum. Small changes in the parameters should not affect my the overall performance. So it has to be very robust. So these are the reasons why we do a design. Okay, design helps you to improve your product. It could be a product also. For example, I have a biosensor and I want to have a good performance of the biosensor. Or it could be a process. I'm doing a fermentation for a biopharmaceutical product, maybe a biopolymer. I want to get the maximum yield. So for all these, we do design actually. Okay. So it's quite a lot used in engineering, chemical engineering, mechanical engineering, the design of experiment, biochemical engineering, bioprocess manufacturing, and so on actually. So we have many variables which I can control. So they are called the X's, or the fundamental variable, or like temperature, pH, pressure, maybe oxygen amount required, carbon amount required, nitrogen amount. Those things which I have control, I can modify them. So those are called independent variable. Okay, so they are also in statistical term, we call it X's. And what happens? The yield changes, or purity changes, impurity level goes down. So they are called the dependent variable, or Y, because when I change X, Y gets changed. So generally, there will be many X's: temperature, pressure, like I said, pH, RPM, and so on. So all of them could be X's, and Y is your outcome, yield, or purity, okay, or selectivity, whatever be the. Okay, so ultimately we want to get a relationship, a mathematical relationship between all the X's, that is the independent variable, to the dependent variable Y. Okay, so like I said, Y could be your yield, for example, yield of a project actually. There are many softwares available to help you to do the design, many softwares, but in this talk, I'm going to talk about how the entire approach of design of experiments is performed actually, or carried out. Okay, what are the underlying theme? So we make the design, and then we go to the lab and collect the data. It could be lab-based in vitro studies, or it could be animal-based in vivo studies. And then we have a lot of, for different X's, I will have Y's, and then I do some analysis. Now I will do maybe t-test or ANOVA test or regression analysis, all those things I'll do. And then I'll derive conclusion. So I'll say these variables are important, these are not important. I'll get a mathematical relation between these X's and Y's. I will say if this particular X is changed, pH is changed, maybe yield goes down. If temperature is increased, yield may go up, and so on actually. So I derive conclusion. So from there, I get the best design. I use it for further in the industrial scales approaches actually. So design of experiments have been used in many areas. Interestingly, even in agricultural, defense, chemical process, biochemical process, manufacturing, quality control. What parameters I need to change to improve the quality of my product, reduce my impurity. For example, I'm manufacturing a drug. I want impurity less than 100 ppm or 50 ppm. So how do I do it? You can use design of experiment approach. Automotive industry, semiconductor industry. So practically in all areas, design of experiments is used. Okay, some of the important paradigm in design of experiments is control is very important. You are comparing with the control. So if I am suppose I have a new blood pressure reducing drug, you will be comparing that drug with respect to old drug, so that you can say this drug is better than that old drug, or this drug is equal to old drug, or this drug is less than the old drug. Okay, so the control comparison is very important. Or you may be comparing with placebos. Placebos means it's not really drug, but it is given to patients so that psychological feelings and effects are eliminated. So always any experiment, there is a comparison with the control, with the old data, with the baseline. So that's very important. All experiments are always is a comparison with the old data, comparison with the old techniques which you are following, comparing with the no drug, okay, comparing with placebos and so on actually. So comparison is always important. So if you are doing the experiments with the new strategy, we have to compare with the existing strategy and say my new strategy is better, or it's equal. So comparison. Next is replication. Replication means repeating the experiments. That's very, very important. That gives you the amount of error that can come in. Even when we do measurements, even temperature measurements, pH measurements, there are always going to be statistical error. Okay, always, because of instrument, because of operator, because of environment, so many reasons actually. That can be 1% error, 2% error, 3%. So always replication is important actually. That is, you repeat at least 3 times, 4 times, 5 times, and get the data. The more you do, better will be your confidence. You will have less of a standard deviation or error in that. So any experiment has to be replicated minimum 3 times. More better, but minimum 3 times. So replication is very important because of operator error, experimental error, instrument error, assay error, ambient condition. Sometimes the ambient summer months temperatures are high, humidity high. So bacteria, for example, grows in one fashion faster. When in winter time, bacteria will grow slower. So ambient also has an effect. So replication is a very important point to keep in mind. It will always reduce the errors. Okay, it will replication will quantify uncertainty. That's very important. So if I get a result, I will know it is plus or minus 2%, plus or minus 5%, and so on. That is why we do replication. Randomization, that's also very important. We have to do in a random fashion so that there is no bias. So generally, if you are doing experiment as effect of temperature, we may do 20 degrees, 30 degrees, 40 degrees, 50 degrees, and see the yield. That's a very, very general way which everybody follow. But that's not, because there is always going to be bias when we do that sort of thing. So randomization is very, very important so that there is no bias. A priori conclusion will not be there. Okay, so for example, if you are testing a drug and you are giving it to different volunteers, you will, when you see certain elder person versus younger person, you may think that the drug might not work on an elderly looking person. That is called bias. Okay, so randomization is very, very important when we do experiments. So how do you do? There are random number generators are there. Computers can help you to do random number generation and so on. Randomization. Selecting volunteers randomly so that we don't have a bias on the volunteers. Okay, so randomization is very, very important. If you are doing animal studies, selecting rats in a random fashion and so on actually, so that there is no bias in whatever you are doing actually. Then stratification or blocking. This is also important. For example, you are doing a study on effect of fertilizer. If I do it in, say, Tanjore in South India or Trichy in South India, there is going to be difference because of the location, type of soil. So you may do different sets of experiments in Tanjore, different sets of experiments in Trichy. So you are blocking the set of experiments in different based on location, geographical location. So that's called blocking. That's also important because you cannot compare results from Tanjore with Trichy because the type of soil, the type of humidity, the type of weather patterns, all those may be different. So it's better to have them separately and do the analysis. Okay. Sometimes you get fertilizers in bags. So there could be some variation between bags. So better to do the study separately with those bags. Okay, suppose you are looking at students' performance in college 1, college 2. So it's better to do them separately and then do some studies on that. So blocking is another aspect which we do, which is important. When you are doing some studies, you want to know effect of certain genetic markers, you may do it based on even different locations in the country also. That's called stratification and blocking. So all these concepts have to be kept in mind when we are doing design. So for example, suppose we are trying to treat 20 males and 20 females. Okay, then in that, half of them will be treated with the drug. The other half will be left untreated. But you can treat only 4 volunteers per day because the lab has got certain limitations. So how do we assign individuals to the treatment, to the day, to the untreated versus treated? Okay, so I will just show you some of the slides. For example, if I take like that, control, that means no treatment, Monday, Tuesday to Friday, 20 people, I do all the controls, and then remaining 20 people where I will give the drug the next week. This is not a very good design. This is a very, very bad design. Why? Because there is no randomization coming into place. This is a very bad design. First week, I will test all the control where I am not giving drug. Next week, I will test all the volunteers who have been given the drug. That's a very bad design actually. Or I will test all the female, then I will test all the male next week. That's a very bad design actually. Okay, so that randomization does not come into when you do the design, which is totally bad. Yeah, imagine you are doing this design. Okay, where you are saying that we will test a drug person who has been given a drug, a female, and then you will be testing the control, that means who has not been given a drug, a male, and so on actually. Okay, T means given treated, C means control, blue means male, pink means female. Okay, so that's one approach one can think about actually, but still this is not a very good design. Look at this. So this is one of the best designs. Say when this is a randomized design, it is quite random. We have mixed up the female and the male. We have mixed up treatment and untreated. If you look at both the weeks, we can even think of another design. This is called more of a blocked design. Okay, so when compared to this type of design, which is very, very okay, unrandomized, completely bad design, this is much better, and this is also much better. So you need to bring in randomization into the picture. So whether it is a treated versus control or male versus female. Okay, so you need to mix up over the 2 weeks. So if you want to do only male, you could have. So you could do 1 week only male control and treated, only female control and treated. But comparing between this group and that group is not correct. You cannot do that actually because it becomes a block. Male alone is a block, female alone is a block. So we have that sort of thing actually. Okay, somebody asked what is the meaning of placebo. So what happens is generally in real life situation, psychological factor plays a very important role. So and even if you don't give a drug, you give some vitamin or something and tell the patient this is a drug, the person gets cured. It's been well documented that the psychology plays a very, very important role. Even sometimes we have also seen, even if you just go and see your family doctor and come back, you may feel much better. That's the psychology. So in order to overcome the psychological factor, what they do is they have a drug like looking thing, which is not harmful. It's unharmful, maybe a vitamin or maybe some even sugar coated pills or something like that. So a patient cannot differentiate between a sugar coated pill versus real drug. So, but both of them will be thinking they are getting the drug. So psychological factor gets eliminated. So if the drug is acting, whereas the placebo is not acting, then it will be only effect of the active ingredient. So psychological factors will not be coming into the picture. So in many many clinical trials, placebo is also given actually. So somebody has asked a question. First we go with the particular age group and next week with some other age group. Then it becomes a blocked design. Comparing the first week group with the second week group will not be possible. But if you randomize a group, like here I have shown male versus female, I have randomized in both the weeks. But if you study only the male in the first week and only the female in the second week, then it becomes a blocked design. We cannot really across between male and female. So you need to, if you want to look at one age group and another age group, you need to randomize into both the set of data actually. Okay. Otherwise, it will become a block design. So you will not be able to compare small one age group with other age group. You can compare only smaller age group within that and bigger age group within that. But if you want to compare everything, then it has to be randomized with respect to age group also. Okay. So randomization is very, very important. Control is very, very important. Replication is also very, very important in design. Now let's look at what is this factorial design. Imagine we are testing some drug for cholesterol lowering. So you want to test with no drug with normal diet, high fat diet. So we have each one with the two sets of possibilities, right? No drug, normal diet, high fat diet. So you may test some people without giving a drug and see the cholesterol level when they are given normal diet. You may look at some people, no drug, but high fat diet. And then you may test some people with drug and normal diet. And then you may test some people with drug and high fat diet. So 4 possibilities are there, right? So this is called a factorial design. So suppose I have 10 patients, I have 40 patients, 10 patients, I may come study on no drug, normal diet, 10 people with no drug, high fat diet, 10 people with drug and normal diet, then 10 people with drug, high fat. So you are considered all the 4 combinations. So that is why it's called factorial. Okay. So this is called a 2 variable, right? Drug, no drug, normal diet, high fat diet. 2 variable, 2 levels, no drug, level 1, level 2. This is also no normal diet, high fat diet. So we call this 2 raised to the power 2 factorial design. Understand? 4 experiments we do. So we have no drug, normal diet. Then we have no drug, high fat diet. And then we have drug, normal diet. We have drug, high fat diet. So 4 possibilities. So we call this 2 raised to the power 2 factorial design. And the 2 in the base is related to the number of factors. Here 2, and then other 2 is in the exponent is the number of levels. So no drug, normal diet, no drug, high fat diet, drug, normal diet, drug, high fat diet. So this type of factorial design, we can learn a lot. Okay, between all the four sets of data, we will be able to understand interaction when you give drug, what happens to a patient with high fat diet or a normal diet, and when there is no drug, what happens with normal diet and high fat diet. So factorial designs are very, very useful. It looks at all the combinations and interactions between drug versus diet actually. Okay, all the 4 combinations. Sometimes what happens is the relationships, maybe when you plot, for example, imagine I am looking at the effect of temperature and pH on a product yield. Okay, so I do 2 temperatures, 30 degrees and 40 degrees, 2 pH condition, 3.5 and 4. Okay, so I am plotting in a paper, let's say temperature 30 and 40 degrees, product yield at pH is equal to 3 and pH is equal to 4. So you get 2 lines, right? So the lines can be like this. The lines can be coming to converge. The lines could be coming to diverge. Okay, so the lines are parallel means there is no interaction between the temperature and pH at all. But if the lines are coming to meet or diverging, that means at one pH, effect of temperature on the yield is in some fashion, but at the other pH, the effect of yield versus pH, effect of temperature versus yield is very different. So the pH seems to affect the temperature versus yield relationship. pH seems to be affecting the temperature versus yield relation. Okay, so there seems to be an interaction between these 2 independent variables, pH and temperature. Whereas here, whatever be the pH, temperature versus yield follows a similar looking graph. So there is no interaction between pH and temperature, but there seems to be some interaction if you have this type of situation or this type. So that means the independent variables seem to be interacting with each other. Okay, so at some temperature, at some pH, temperature affects the yield in one fashion. At some other pH, temperature versus yield is affecting in some other fashion. That is called the interaction effect. Okay. From which design? Okay, which design? Why acidic pH? I don't know. Yeah, so some of these fermentations, the pH is in the acidic range. So we go down some of the pH. So other points we need to consider is in clinical trials, they do something called blind and double blind. What they do is there should not be bias by the doctor himself. So doctor himself should not, suppose doctor sees a very sickly looking person, if he's giving drugs, he should be giving him more. Or if he looking healthy person, doctor will think the person is healthy. So he may be psychologically feeling, why should I give the drug? So doctor may have some a priori notion or feeling. So we don't want it. So the doctor also should not know whom he is giving to. Doctor should not know whether he is giving a placebo or a drug to a patient. Patient also will not know whether he is getting a placebo or a drug, and that is called double blind. So in most of the clinical trials, they always follow the double blind approach. Okay, that means doctor will not know whether he is giving a real drug or a sugar-coated placebo. Patient also will not know whether he is getting a drug or a placebo. So it's completely psychological effects, other feelings, everything gets eliminated. Okay, so all the clinical trials you must are always carried out in double blind. So when they are even doing these vaccine trials and so on, they would have always followed this set of approach, which is called the double blinds. Another important point, are the subjects you are studying really representative? Okay, so suppose I am going to do a clinical trial for a vaccine in India. I may select some people in the upper class. I may select some people in the middle class. I may select people in the lower class because maybe their diet habits are different. So that way we try to cover the entire Indian population. It has to be representative. We should not be doing drug trial only on one particular class of people, because the food habits, the protein levels, the other factors may be differing. So representativeness of the testing is also very important, actually. And then, okay, so to sum up, it has to be unbiased, randomized, blinding, precision. So we need to do a lot of replications. Now we have to be very sure there is errors are taken care of. We have to protect against mistakes. It should be applicable to the entire. So if you are testing a vaccine, we may have to test throughout India, different states, the upper class, middle class, lower class. That way it becomes more representative. Okay, not just South India alone or not just North India alone. Then it's not a representative population. So before vaccine trials, they would have done all these actually. And then we should also be able to estimate uncertainty. We should be able to tell whatever results I get, it will be within this plus or minus 3% or plus or minus 5%. Okay, that is also very important. So this is how good designs are done actually. So we need to collect all the X's or the independent variables which are necessary for my design. As a chemical engineer or a biochemical engineer, you have already knowledge. So as a biochemical engineer, I will tell temperature, pH, RPM, oxygen bubbling, maybe amount of carbon, amount of nitrogen. All these will have effect on my biopharmaceutical product yield. Okay, as a chemical engineer, I may say, when I'm doing a reaction, amount of catalyst I add, how much pressure I do, how much temperature I do, pH might not come into picture, temperature, RPM maybe. So these factors may be affecting my yield. So the domain knowledge is very, very important. So you may already know you are a mechanical engineer and you are looking at some performance of a particular equipment. You know what are the X's or the independent variable that will affect my Y. So you already have. So statistics cannot help on that actually. Statistics tells you how to vary each of the variable, but the domain knowledge is very, very important. As a mechanical engineer, you know which parameters. As a biochemical engineer, I know which parameters have an effect on yield. Okay. As other type of engineer, you have a good domain knowledge. Imagine you are delivering this is a courier. So packet, the person is delivering a courier letter to somebody. The courier company will know which parameters will affect my delivery time, because okay, what type of transport I am using, what's the speed at which I am going, which route I am following. So he will already know, and he will generally tell the delivery boy this. For example, even your delivery of say food deliveries, they have an app by which they find out the closest route. If there is traffic jam, it tells them, and so on. So these factors have an effect on my delivery time. But there are many factors which we do not have control on. Okay, suddenly there is a VIP coming and that road is blocked. Okay, so that's a factor where you don't have. So there are some controllable variable, there are uncontrollable variable, okay, which you not have control. Okay, maybe there is a road repair, so it gets delayed. VIP coming, so blocked. Whereas the vehicle I use, how good my vehicle is, how good I am delivery. So those things are controllable X's. There are some X's which are uncontrollable X's, and there are random variables. That's third one. Third one is random variables like monsoon coming. So there'll be a lot of rain on the way. If we are in a northern country, there could be snowfalls. So those are all variables which we call environmental variables. You have no control. Even in my bioprocess, I am doing a fermentation. Environmental variable could be humidity, because bacteria grows differently in different environments. Temperature, ambient temperature, not the reactor temperature, ambient. So those things I have no control. So they are uncontrollable variables. They are called, we call it environmental variables. So in any process, you will have environmental variable, controllable variable, uncontrollable variable. Okay, so only some variables you can control. You can't control everything. Even delivery of your pizza or letter, you can't control whether it's going to be a road repair or whether a VIP is crossing that place and so on. Actually, so in any area you have these variables that can be controlled. Temperature I can control, pH I can control, pressure, oxygen bubbling rate, RPM of my motor, amount of carbon I am adding, amount of nitrogen I am adding, amount of micronutrients I am adding. All these are controllable, like ambient temperature, ambient humidity, even electrical fluctuations which will affect my motor or something, or which will affect my pump. Okay, those things I have problem actually, which can become uncontrollable. So that knowledge is also very, very important for us to do actually. Okay, there are two types of approach. One is called the screening design, other is called detailed design. So in screening design, we will select many factors, many factors, 10, 20 factors, and we do quickly some designs, and then we eliminate factors which are not important. So that's why it's called screening. And we pick up some factors which we think is important, and then we can do a detailed design. Okay, so that's called screening design, detailed design. Okay, screening design, you may take many factors, you will just do some experiments, and of course you follow the design principles, do some experiments and identify variables which are not important. So you may start with 10 factors, and you may end up with 3 factors in screening design. With the 3 factors, you may do a very detailed design. That's possible actually. Okay, and then operability is also important. See, pH can change quite a lot, but I may be interested more in the pH of 5 to 7. Okay, so that's what I'm interested in. I'm not interested in the entire range of 0 to 14 and so on. So the range of operability within which you will work, because all your real life situation also will be between say pH 5.5 to 7 or something like that, right? So you'll be working in that range. So that's called the region of interest as against region of operability. I may be able to change the pH, but then I'm only interested in 5.5 to 7 pH. So that is my region of interest. Okay, so I talked about different types of factors which can be controlled, factors which cannot be controlled, environmental factors. All these are very important for us to know, actually. All these are very important. Even fluctuations in your electric current some electronics could start drifting because of some fluctuations in your voltage. Those are maybe you might not be able to control immediately. You may be thinking of having a UPS and so on to control the fluctuations. One approach is doing one factor at a time. That means you change temperature from 30, 35, 40, 45 and see the yield. Then you change pH 3. Say 3.5, 4, 4.5 and see the results at the constant temperature. That's called one factor at a time. That's not a very good design because we will not know the interaction between temperature and pH. So doing one factor at a time, keeping the other factor constant, then changing the other factor, keeping this factor as a constant. It's not a good design, and that is called a one factor at a time design. Okay, one factor at a time design, which is not a good idea. So in a factorial design, which I showed you before, like no drug, and normal diet, fat diet. Okay, so factorial design, say I have two factors A, B. I have two levels like no drug, or normal food, fat food. I can call it low, high. So first experiment could be low in A, low in B. Second experiment could be high in A, high in B. Third experiment could be low in A, high in B. Fourth experiment could be high in A, high in B. For example, if A is my temperature, the levels of temperature is 30 and 40, and B is my pH, say 5 and 6. So low means I may do at 30 temperature and 5 pH. High low means I may do 40 degrees temperature, 5 pH. Low high means I may do 30 degrees temperature, 6 pH. High means I may do 40 degrees temperature, 6 pH. So I cover both systematically combined together. And this is called a factorial design. Two factors A, B, that is temperature and pressure, pH, and two levels, low and high. So two factors, two levels. Okay, this is called a 2 raised to the power 2 design. 2 raised to the power 2 means 4 runs, right? That's why it's called a factorial design, 2 raised to the power 2. You can have two factors like temperature, pH. I can put temperature, pH, and also pressure. That could be third factor, A, B, C. And each one of them modified in high, low, high, low. So that will become 3 raised to the power 2. Right? 3 factors, each at 2 levels. That could be 3 raised to the power 2 is 9 experiments. So two levels, 3 experiments. So 8 experiments actually, 2 raised to the power 3. So 2 relates to the levels, and this 2 relates to the factors. This 2 refers to the levels. Here we have low and high, and this 2 refers to the factors, factor A and B. Okay, so temperature and pH. So if I have temperature, pH, pressure, 3 factors, but 2 levels only, lower and higher. So it will become 2 raised to the power 3, 8 experiments and so on. Okay, so if you imagine you have 2 factors here, they are given an example of time and temperature. So they have done 4 experiments. 80 degrees is the lower time, 170 degrees is lower temperature, 90 degrees is higher time, 170 is lower temperature, 80 degrees is lower time, 180 is higher temperature, 90 is higher time, higher temperature. So 4 experiments they have done. Imagine they got some results of some yield, say that they call it response or Y or dependent variable. You can call any names for that. So what is the effect of time on the response? We will add these 2 runs, 46 plus 79.5 by 2 minus 58.3 plus 47.7. So effect of time is there is an increase in 9.85. Got it? So effect of time means this plus this divided by 2, this plus this divided by 2 minus. So that's what they have done. 46.2, 79.5 minus 58.3, 47.7. So effect of temperature temperature, you add these two because this is lower temperature divided by 2. You add these two divided by 2. So this minus this. So 47.7 plus 79.5 by 2 minus 58.3 plus 46.5. So effect of temperature, there is an increase in the yield by 11 units. I'm not saying what the units are. So this temperature has a higher effect than time here. Okay. So this is a problem which shows you how to calculate the effect of each of the variable. It shows you a 2 raised to the power 2 design. That means 2 factors, time and temperature, 2 levels. That means lower level and higher level. So it's a four experiments, 2 raised to the power 2 experiments. Okay, so if I have only one variable, I may do say only temperature alone. I may do at 2 conditions, right? Say 650 degrees, 60 degrees. So I'll be doing 2 experiments. If I have 2 variables like temperature and pH, I will do low, 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 high, high, low, high, high. So 4 experiments, 2 raised to the power 2, 4 experiments. If I have 3 factors like temperature, pH, and pressure, so it will be like 2 raised to the power 3 experiments. The 3 represents the factors, the bottom 2 represents the levels. So that is 8 experiments. It's like a cube. So each is one factor. So factor A, factor B, factor C. Understand? So each one at 2 levels. So this 2 represents the factors. Sorry, this 2 represents the levels. The 3 represents the number of factors. You can show it in a very analytical form also. For example, if you have 2 factors, low, low, we call it -1, -1. High, we call it +1. -1 means low, minus is low, plus is high. So -1, -1, +1, -1, plus -1, +1, +1, +1. So 4 experiments. Instead of saying it as low, low, instead of calling it low, low, high, high, we put it in a numerical form. So low is -1, plus means high. So if you have 3 factors, 2 levels, 2 raised to the power 3 is 8 experiments. So you'll have -1, -1, -1, +1, -1, -1, then -1, +1, like that. All combinations will come. So it is 8 experiments. Agreed? Okay, so if you look at 2 factors, A, B, 2 levels, 2 raised to the power 4 rands. So -1, minus, +1, minus, then minus, plus, plus, plus. So if you want to look at the interaction of A and B, like I showed you, I have temperature and pH interaction. We can do A, B. So minus into minus, if you multiply, it will become +1. Plus into minus, if you multiply, this will become -1. Minus into plus, if you multiply, this will become minus. Plus into plus will become +1. So AB will be like -1, +1, +1, -1, -1, +1. So similarly, if you have three factors, you can have AB, AC, BC also. And then you can also have ABC also. So we can look at all the types of interactions when you do this type of factorial designs rather than one variable at a time. Okay, so again, coming back to the same, this one, come back again. Two factors, A and B, 2 levels. So -1, -1, -1, -1, sorry, +1, -1, -1, +1, -1, sorry, +1, +1. So 4 experiments. And look at this. There will be 2 minuses, there will be 2 pluses. There will be 2 minuses, there will be pluses. That's called a balanced design. So you are doing, same number of experiments as you do at the lower level with respect to the higher level. You are not doing more experiments in the higher level and less experiments in the lower level. Suppose I am temperature lower level is 50 degrees, higher level is 60 degrees. It's not that you are doing more experiments at 50 lower level or you are doing more experiments at 60 degrees, but you are doing equal number of experiments. That's called balanced design. So there is no bias at all at any temperature. This is very, very important in statistical DOE. The balancing is very important. The number of experiments you do at each level should be equal. There should not be any bias at all. I do some experiments at some temperature and some less, or I do more experiments at some pH and do it less in some other pH. That's totally wrong actually. That's called balanced design. So any design should have that balance, number one. Another one is, I said this minus for AB, you can multiply this minus into minus is plus, plus into minus is minus, minus into plus is minus, plus into plus is 1. That is AB, right? Now, even AB, a number of minuses are equal to number of pluses. You see, there are 2 minuses, 2 pluses. That's called orthogonality. So any design should be balanced as well as orthogonal. So when you design experimental strategy, it should be both orthogonal, it should be balanced. That's very important actually. Okay. So all of them will be like that. So if you look in the previous page, we did ABC. If you look very carefully, number of minus in A 2, 3, 4, right? 4 minuses. Number of plus 1, 2, 3, 4, right? Equal. Same thing for factor B. If you look at it, no, number of minuses 1, 2, 3, 4. Number of pluses 1, 2, 3, 4. For C also, 4 pluses, 4 minuses. So it's a very balanced. For orthogonality, AB is given here, right? So AB is here. So look at the number of minuses here. 1, 2, 3, 4. Pluses 1, 2, 3, 4. So even the interactions are also equal. So these are called main variables. These are called interactions. So the number of experiments you do for main variable at one level versus other level is equal. Number of experiments you are looking at in the interactions are also equal. So that is called orthogonal. So any design you plan, it should be both balanced and orthogonal. That's very important. Yeah, that way there is no bias. You are overdoing experiment at some level, underdoing some experiments at some other level is totally unacceptable actually. That's important point to keep in mind actually. Another thing is you will be able to study interactions also. Like as you can see, you know, when we do these 4 experiments, they can also study AB because AB is also balanced. Minus plus, plus minus minus, minus plus is minus, plus is plus. So that also is balanced. So we can look at how AB is interacting. So if temperature was say pH, is there an interaction between temperature and pH? That sort of studies can be nicely done with this type of designs which I have shown you here. So balancing and orthogonality is very important actually. But there are some drawbacks of factorial design. Like if there are 2 factors, 2 raised to the power 2, 4 experiments. If you have 3 factors, like temperature, pH, and pressure, 2 raised to the power 3, you have to do 8 experiments. Suppose if you have temperature, pH, pressure, and the carbon amount, then it becomes 4, right? 2 raised to the power 4 is 16 experiments. So if you have 2 raised to the 5 factors, the temperature, pressure, pH, carbon, nitrogen, that is 5 factors, number of experiments become 32. So number of experiments keep increasing, huge. It becomes very difficult. So doing experiment is time consuming, also very expensive, because I'll be wasting chemicals and so on in my lab, right? So we need to consider those aspects also. So there came something called fractional factorial designs. Okay. So what you do is you don't do as many experiments, but do very scientifically, very technically reduce the number of experiments. So you do less number of experiments, but you get the same knowledge. That's called fractional factorial. So you can, instead of doing 16 experiments, you may even do 8 experiments, but you select in a very strategic manner so that you get all the knowledge required or all the information required. That's called fractional factorial design. So there are different types of fractional factorial design. Because want of time, I will not spend much time. So just like factorial designs and fractional factorial, other designs for screening, there is something called placket Burman design. There is something called fold over Koshal design, something called Latin square design. There is something called Taguchi design. So many types of designs are there. All these are generally we use it in screening. Like I said, screening is first you do with many factors. You get rid of some of the factors which you don't think is very important, and then you later on do a very detailed design. So that screening design, there are many types of approaches are there. So there is a full factorial design, and then fractional factorial, which I just mentioned, to reduce the number of experiments. Then there is something called placket Burman design. There is something called fold-over Koshal design, Latin square design, Taguchi design. All these are various designs which can help you to plan your experimental strategy for screening purposes. Okay, so many softwares give you all these information. Because of want of time, I'm not spending much time on that. So if you look at excuse me. Yeah, this is called a placket Burman design. So suppose I have 7 variables. For example, temperature, pressure, pH, carbon amount, nitrogen amount, manganese amount, and zinc amount. We use manganese, zinc. These are all called micronutrients for bacteria to grow in fermentation. So imagine I have 7 variables. I can even do 8 experiments. I can get some information about which variables are important, which are not important. So I can use this as a screening strategy. I can eliminate out of 7, 3 or 4. So I will end up with only 3 important variables. There I can do a very in-depth design. So this is a placket Burman design for 7 variables. So similarly, you have placket Burman design for 11 variables. Okay, RPM, maybe pressure, maybe other micronutrients, maybe so many other factors could be brought in. So you may have 11 variable situation. So with 12 experiments, we will get knowledge about which ones are important variables, which are not important, which can be eliminated. So that is called a placket Burman design for screening purposes. So these designs, many designs, like I said, are available for you to do for screening purposes actually. And then this is called a fold-over Koshal design. Okay, and they give you how to run these experiments. So many experiments, 10 experiments for 4 variables, 10 experiments for 4 variables. Then it's called a fold-over design. Again, this is say 4 variables, 8 experiments. But all the designs will always consider balance and orthogonality. Even in fold-over design, if you see the 4 pluses will be equal to 4 minuses. Check everywhere. Balancing and orthogonality are very, very important in the design of experiment study. This is called a Latin square design. Okay, this is a Latin square design. Taguchi designs. These are Taguchi designs are already available in literature, so we can pick up a different type of Taguchi design depending upon the number of parameters you have. If I have 2 parameters, what type of design? If you have 3 parameters, what type of design? 8 parameters, like that, and they already give certain design strategies. You just pick up and then we can prepare the design and run the experiment. But now many software, Minitab, for example, gives you automatically design. So if I have, say, 5 variables, I want to do a screening design, each one at 2 levels, it will automatically give you 2, 3 designs. You can select the best one based on your knowledge. Like that, there are softwares which can also do the job for you, okay, for screening design purposes. So screening designs, we start with large number of variables, we reduce the variables to a small number, and then we can spend more time looking at in a very, very detailed thinking. Okay, screening designs are also called linear designs because you do only at 2 levels, right? It is like a point temperature 50 degrees, 60 degrees, pH say 5 and 6. Okay, 2 levels. Time could be 80 minutes, 90 minutes, 2 levels. So that's why they are called linear designs. We can also have non-linear designs if we do experiments at 3 levels. 3 levels means you can fit a quadratic relation. You can even have 5-level designs. Okay, they are called central composite design. So those are called non-linear designs or quadratic designs and so on. Whereas these designs are called linear designs. Okay, these are all called linear designs. So these are all Taguchi designs. Will not spend too much time because of want of time. Second order designs or quadratic or a higher level design, unlike the linear designs which are done at 2 levels. One of the important higher level designs, that's called a central composite design. Okay, CCD they call it. So you have, say, 3 variables. I can put it like a cube, 3 variables, no temperature, pH, pressure. Each one of them is temperature, pressure, pH. Okay, temperature at one level, temperature at another level, pH at one level, pH at another level, pressure at one level. Pressure. Okay, in this particular, say, cube, you have 8 points in the corner of the cube, correct? 8 points in the corner of the cube, and there will be a central portion of the cube, so 9 points. Okay. In addition, you will do outside the cube in each side of the face of the cube. That will be 6 points. So totally 15 points you do. Okay, 8 points and the corner of the cubes, the center of the cube, right in the middle, and then from the face of each face you do outside from all the sides. So 6 faces. So totally 15 experiments you'll do for 3 variables. But the beauty is you are doing at 5 levels. So if there is a temperature, you are doing at 5 different temperatures. pH means 5 different. Pressure means 5 different. So we can develop a 4th order equation also, because if you have a five temperatures, you can get a 4th order polynomial relationship. Okay, but you are doing only 15 experiments. So these type of designs are very, very efficient. 15 experiments, 3 levels. We are looking at that, I say, temperature at 5 different levels, pH at 5 different levels, and so on. So these CCD is one of the most widely used design for higher order, because the number of experiments are low, but you get more information about the process which you are studying. Temperature at 5 levels, pH at 5 levels, say pressure at 5 levels. But when you do only 15 experiments, that's the greatness of this particular design. This is called central composite design. There is another design that's called 3-dimensional design. That's called, this is also higher order design, box Bencan design. I'm showing 3-dimensional because I am looking at 3 variables. But if you have multiple 4 variables, 5 variables, you will have a 5-dimensional cube or something. Okay, 3-dimensional cubes are easy for us to see. That's why I'm showing all 3. So another design, higher order, is that's called box Bencan design. Just like central composite, we have box Bencan design. It has a different type of philosophy in the process. Okay, these points are called star points, which are outside the cube. So you have the cube, 8 corners of the cube, and one central point. That's called the central point. In addition, you are also doing experiments outside the cube, and these points are called star points. And there is a strategy. There is a star point. So there is a strategy of selecting the star point. You can't just put any point and call it star point. Outside the cube, that's called star point. Okay, there are strategy, there are equations, mathematical relation, which tells you how to calculate the star points and so on, actually. So it's not any point you take outside the cube, depending upon the number of parameters. There are some equations. Again, I don't have time to spend how to calculate that based on certain optimization and so on, actually. Okay, you can also factorial design. We talked about 2 raised to the power n. 2 is the number of levels and n is the number of factors. We can also have 3 raised to the power n designs. That is 3 levels, n factors. Okay, but the number of experiments increases a lot. 2 factors means 3 raised to the power 2 is 9 experiments. 3 factors means 3 raised to the power 3 is 9. 3 into 3 into 3, 27. So look at this, number of experiments increases. Whereas if you do a central composite design like this, yeah, the number of experiments are extremely manageable. Look at this. Now for 2 factors, you'll do only 9 experiments. 3 factors, you'll do 15. Whereas in 3 raised to the power n design, you'll be doing 3 raised to the power 3, you'll be doing 27. If it is 4 factors in CCD, you'll do only 25 experiments. But whereas here you will be doing 81. So it goes up exponentially. Whereas CCD is very manageable, actually. So that's the beauty of central composite. All these designs you do only after doing the screening design. So you do the screening design, eliminate as many factors as possible, come down with the most important factors. Like I said, I may think of temperature, pressure, pH, time, RPM, carbon amount, nitrogen amount, manganese amount, zinc amount. So I have 10 variables, but all 10 might not be very important. So I do a screening design and I finally find carbon is important, pH is important, manganese is important, and zinc is important. So I will spend more time. Maybe I will do a CCD with 25 experiments. Okay, so this is how you do in your design strategy also. And then you have the box Bencan design. So how the design has to be done in a 3-level design, just like in 2-level we say -1 +1. In 3-level we say -1 +1 and also 0 also. 0 means that's the central point here. The red color is 0. So if the time temperature is say 30 degrees, -1 could be 25 degrees, +1 could be 35 degrees, right? Like that, so this is box Bencan design strategy. And then this is for 4 factors, 5 factors. Then this is central composite design for 3 factors, and so on. So there are so many designs. Like I said, softwares are there to help you. But my talk is meant for you to understand the concepts of how these designs are done. What are the important points one needs to keep in, especially the balancing and the orthogonality, why randomization is important, why replication is important, why blocking is important, control, placebo. So those concepts are very, very important when you start planning your design as such. Okay. So I think I will stop with that. If there are any questions, I've answered some questions during, but if you have any other questions, you may ask me also. I'll be pleased to answer.
Students, the session is open for discussion. You can ask.
Yeah, if you have any questions. I had to squeeze the whole thing in 1 hour, but the design of experiments, one could talk for about 5 to 6 hours. If you have heard of NPTEL, which is MHRD initiative, and all the IITs have joined together, and they have video courses, many hundreds of video courses on different topics, ranging to about 40 lectures. I have a course called Biostatistics and Design of Experiment. So if you are interested, biostatistics, you could go through those videos, or you could register for the course, and you could even take the exam and get a certificate also. So there I cover design of experiments in about 7-8 lectures actually. Yeah. If one wants to go more in detail into these concepts.
Someone has asked, what is the meaning of word stratification?
What is the meaning of, stratification is called blocking. Okay, stratification is also called blocking. What we do is we combine certain aspects into one. We don't compare between this and that. For example, like I said, I am testing a fertilizer with certain carbon, with fertilizers, NPK, nitrogen, phosphorus, potash. So I'm comparing this fertilizer with some old fertilizer. So if I am doing some experiments based on quantity of fertilizer and a ratio of NPK, I may do it in Trichy, in some agricultural field, I may do in Tanjore and so on. So I would like to keep the experiments I have done, results I have done in Tanjore separately and Trichy separately. So that is called blocking and stratification. So I do not compare across, okay, because there will be variations between the climatic conditions, say maybe in Tanjore and Trichy. I have not brought those factors into the picture. Maybe soil variations could be there, humidity variations, weather variations, all those could be there. Okay, so I will not be able to compare. So I will do experiments in Tanjore alone. So all the results, whatever I have done, I do the analysis only in Tanjore, then only in Trichy. So sort of I have blocked them separately. I stratified them separately. I have not done it as a total. Okay. So that is one strategy you may adopt. because you can't have control of same conditions in Tanjavur and say Trichy, because so many variations are there based on climate, humidity, and so on actually. Okay.
One more question has come. Is
Okay.
Taguchi table used only for biochemistry purposes?
No. I have seen examples of Taguchi in mechanical engineering. Many things. So each one, there is nothing like only one area. You have many designs. You can make your own choice based on how many experiments you have to do. What combination, say AB, I said AC, AB, which combinations you are interested to know. That means, should I know if there is an interaction between temperature and pressure or temperature and pH, which ones are important I want to study. So that design gives you that information also. Like that, based on your domain knowledge, based on number of experiments, you can select the design. Sometimes Taguchi design might not have so many. Suppose I have 20 so many variables and I want to do approximately this many number of experiments, let's say 2 levels. I might not have an optimum set of experiments. I may find it in, say, placket Burman. I may do that. For example, placket Burman screening designs are very good if your number of variables are like 7, 11, like that, because they are based on 4i. 8 experiments, so 7 variables, 12 experiments, 11 variables. So if I am somewhere near 11, then placket Burman is very efficient. 12 experiments, I can do a lot of screening when compared to your normal factorial experiments. Like that, there are many strategies available for you to select based on having minimum number of experiment, maximum knowledge or information I should be getting. Anything else? Yeah.
One more question is there.
Yeah.
Which design is better?
Like I said, no, you can't say anything on that. My goal ultimately is minimize the number of experiments, number one, but I should get as much knowledge, information as possible. I can minimize very little, totally, and then I will not get any information. But based on my domain knowledge, like I know I want to study, say, the temperature and pH may have an effect, combination. So I want to study that. That is AB, for example. AB combinations I want to know. So which designs give me that? And which design gives me minimum number of experiments. So how many variables I have. So I gave you the previous about placket Burman. If I have 11 variables, placket Burman of 12 experiments is very good. Whereas if I have 7, if I have, say, 10 variables, placket Burman of 12 experiments is not efficient because I have to keep something called dummy variable and all that. So I may look at some other design. So depending upon number of variables I am looking at, depending upon number of levels I am looking at, like 70 degrees, 80 degrees, 90 degrees, that is 3 level. 70 degrees, 80 degrees is 2 levels. So some of them I may look at 2 levels, some of them I may look at 3 levels. So depending upon that, you select the design. But my first goal may be minimum number of experiments, because everybody wants to do less experiment. But I should not lose information when I do minimum number of experiments. That's also very important for us to keep in mind.
One more question has come. Is in placket Burman table, we use 2 types of variables. One is real variable and the second is dummy variable.
Yeah. Correct. Why dummy? Like I said, if I have 11 variables, placket Burman goes by 4, 4, 4. 8 experiments, 12 experiments, 16 experiments, like that. They have given designs only for that. Suppose I have 7 variables, I can do a 8 experiment placket Burman. I can choose from the table. Suppose I have to do 6 variables only, but I want to use placket Burman. It is meant for 7 variables. 8 experiments is meant for 7 variables. So the 7th variable is called a dummy variable. It has no meaning, but it's a dummy. So placket Burman is very efficient. If I have 7 variables, 11 variables, 15 variables, no, it's very efficient to choose. So if we have 10 variables or 14 variables, then one of them has to be a dummy. If I want to choose placket Burman, if I want to choose. So I have to look at some other design. So ultimately I want to do less number of experiments. So I can look at each design and see which one gives less, and some combinations, which one gives me what I want, and so on actually. Any other doubts? As real variable change according to time. No, any variable, the independent variable you have control, right? Time, temperature means I set the reactor at some temperature. These are all controlled variable. Excess, that is independent variable. Dependent variable is like your yield based on your independent variable. That's why. Okay. So temperature, if I set on my reactor, it will always be constant. So it's not going to drift or change, right? So if pressure I set in my reactor, the pressure constant. If I'm setting RPM, I'll set the RPM using my electric motor. That's constant. So it's not going to change. I have control, right? Those are all called controllable variables or excess or independent variable. This is the terms we use. Excess, independent variable, controllable variable. If I'm adding some carbon to my fermentation, I will add 1 gram means I will always add 1 gram and do the experiment, right? I have control. Okay. So all the x's I have control. X, all the x is called the independent variable. I have control on the x's. Y is, that is dependent variable, I don't have. Based on x, it will change. And then there are some variables which are environmental variables which nobody has control. The humidity, today's humidity was nobody has control like that here. Okay.
Any other questions? If no more questions, we will thank Dr. Professor Mukesh for joining us and elaborating us on experimental designs. Thank you.
Yes.
Thank you so much, Professor,
Okay.
for
Okay,
joining
sir.
us.
Okay, sir. Thank you. Thank you very much. Thanks to everyone. Bye-bye.
Thank you.
Thank you.
Yes.